Hello, we move to the second section of this short course, and in this one I will prove several statements, two of them about divisibility and one inequality, without using induction. Let's start. Proving divisibility without using induction, problem number 1. And this first one in this section is prove that for each natural number n, we have n to the third minus n is divisible by 6. And now, this very problem was solved in the course Mathematics Proofs by Induction with help of mathematical induction. But actually the proof with other methods, which I will show you now, is much nicer. So this is why I would like to show you this second method of solving this problem. So first, a very simple observation. If you just look at integer numbers and you look at remainders in division by 2, you can only have two different types of remainders, 0 or 1. 0 if your number is even, and 1 if your number is odd. Nothing strange here. So if you look at integer numbers like this, you see that every second is even, and and you can write them here. I started with a 0, then 2, 4, 6, and so on and so on. Each even number can be written as 2 times some integer, right? So every second number is even, of course, if we look at integer numbers. And every second is odd, and they can be written in this way. So you see that the remainder can only be 0 in the case of even numbers, or 1, right? No other possibilities. And number of remainders in division by 3 are 3 possibilities, 0, 1, and 2. And if you wonder why I'm interested in divisibility by 2 and by 3, my answer is, well, because I have to prove divisibility by 6. And 6 is equal to 2 times 3. So 6 is the product of 2 and 3. And because 2 and 3 are both prime numbers, so in particular they are relatively prime, they have no common divisor, then I can separately verify divisibility by 2 and separately divisibility by 3, and these two combined will give me divisibility by 6. So let's have a look at integer numbers. Every third number is divisible by 3. Right? And you can write them here again. I started from 0, so 0, 3, 6, and so on and so on. These can be written as 3 times some integer. Every second has a remainder 1 in division by 3, so this means that they can be written like 3 times some integer plus 1, and the remaining numbers will have a remainder 2 in division by 3. And this what you should, so I told you actually more than you need for solving this particular problem, but this is very nice to have this image in your head when you work with divisibilities, that they are just 3 possibilities basically when you look at divisibility by 3, and you have just 2 possible cases in case of divisibility by 2. And what is important for us now is that every second number is divisible by 2, every third is divisible by 3, and so what you also see in this picture, in each group of 3 consecutive numbers, which means that 3 numbers which follow directly after each other in the set of integer numbers, there will be 1 divisible by 3. So if I take these 3 numbers, the third one will be divisible by 3. If I take these 3, the one in middle will be divisible by 3. And if I take these 3, it will be the first one. So, and regardless how I pick these 3 consecutive integer numbers, there will always be one, exactly one divisible by 3. Okay, so now I have prepared you for everything. And now comes the solution, which is really the nicest solution ever. You see, I take now any natural number n, and I will rewrite n to the third minus n in the following way. I will factor out n, and when I factor out n, in my parentheses, I will end up with n squared minus 1, right? Because n times n squared is n to the third, minus n times 1 is minus n, right? So this is true. And now I can apply this formula, which I have applied several times in this course already, that a squared minus b squared is equal to a minus b times a plus b, the formula for the difference of two squares. And this time I will apply it with a equal to n and b equal to 1. And I will apply it here. So n squared minus 1, 1 is equal to 1 squared, right? 1 is its own square. It will be equal to n minus 1 times n plus 1. So I can write here that it will be equal to n minus 1 times n plus 1, where this factor here is equal to the product of these two factors. But you understand why I ordered them in this way, right? Because now I see that n to the third minus n is equal to the product of 3 consecutive integer numbers. n minus 1, the next one is n, the next one is n plus 1. And because n to the third minus n is the product of 3 consecutive integers, then at least one of them is even, maybe even 2, but you don't know it, but at least one of them is even, and exactly one is divisible by 3. So, and that's all. Now I see that n to the third minus n indeed is divisible by 6. So the conclusion is n to the third minus n is a product of 3 consecutive integers. So one of the factors is divisible by 3, and at least one of the factors is divisible by 2. And as 2 and 3 are relatively prime, they have no common divisors, it means that n to the third minus n is divisible by the product of 2 and 3, and this is 6. This is exactly what we were supposed to show. Thank you for watching. Bye bye.